11.2 Alkanes. A large number of carbon compounds are possible because the covalent bond between the carbon atoms, this carbon to carbon, is very strong. And so this is why they make such a backbone of living molecules, anything that once lived. So the goal is to write the IUPAC names and draw the condensed structural and line angle formulas for alkanes and cycloalkanes, which you probably only know a couple of those words there, and we will learn those in this section. Now, alkanes are hydrocarbons that contain only carbon to carbon and carbon to hydrogen bonds, hence the word hydrocarbons. They are formed by a continuous chain of carbon atoms. They are named using the IUPAC system. They have names that end in -ane, and that -ane ending means that it's all single bonds. They use Greek prefixes to name some of the carbon chains, like 5 and above. You do need to know the first 10 prefixes. Let's look at the next slide. So, we need to memorize the prefixes representing molecules with 1 to 10 carbon atoms. So, meth, so here on table 11.2 is the first 10 alkanes. They are all single bonds, so that means the ending will all be -ane. But for 1 carbon, the prefix is meth. For 2 carbons, the prefix is F. 3 is prop. 4 is bute. 5 is pent. 6 is hex. 7 is hept. 8 is oct. 9 is none. And 10 is dec, which several of those prefixes you probably already know. So when I say you got to memorize all 10, yes, you need to know all 10, but maybe only 3 or 4 of them do you actually have to memorize. You probably know all the others. Now, the formula for figuring out how many hydrogens there are in an alkane is however many carbons there are, the amount of hydrogens are 2n plus 2. So let's say that you had 5 carbons. To figure out how many hydrogens it would be 2 times 5, which is 10, plus 2, 12. It would be 12 hydrogens. In a condensed structural formula, each carbon atom and its attached hydrogen atoms are written as a group. A subscript indicates the number of hydrogen atoms bonded to each carbon atom. A condensed structural formula of butane has 4 carbon atoms. Now we have a CH3 dash CH2 dash CH2 dash CH3. So let's see why it's that way. We learned in the last section that carbon always has 4 bonds. So this carbon is attached to the next carbon, which means this first carbon then has room for only 3 hydrogens. So it'll have 3 hydrogens, and those 3 hydrogens are shown bond to it. Now then, this second carbon is attached to the first carbon on the left and the second and the third carbon on the right. So that means there's only 2 spots left for bonds, so that's why it's only going to have 2 hydrogens. Ditto for the next carbon. And then for the last carbon, the reason why it has 3 is because the last carbon only has 1 bond to another carbon. That means it has room for 3 more hydrogens. So because it's going to have a total of 4 bonds. And so we'll have 3 hydrogens here for butane, assuming that this all has just single bonds. Now notice how the hydrogens attached to a particular carbon are written directly after it. Or it can be simplified without dashes like so. CH3, CH2, CH2, CH3. All different ways to show the exact same writing of the carbon and hydrogen molecule. So we have carbon with its 3 hydrogens attached to something could also be written as CH3. This particular carbon that is attached to 1 atom here and 1 atom here, probably a carbon here and a carbon here, it has rooms for 2 hydrogens, so it would be written as CH2 with the attachment left and the attachment right. Now, alkane compounds can also be represented by their molecular formulas, which just gives the total number of carbon and hydrogens. Doesn't tell us a thing, except that tells us how many carbons and how many hydrogens. So in this case, a molecular formula would be C4H10. Or another way would be the line angle formula. I call it the zigzag formula, which shows the carbon skeleton in which carbon atoms are represented at the end of each line or each corner. So here's a corner or an end. So 1, 2, 3, 4. So this would be butane. Why? Because it's got 2 corners and 2 ends. So that's every time we have that, that's going to be represent a carbon item. So you now know that an alkane molecule can be represented in several ways: the molecular formula, ball and stick model, expanded structural formula, a condensed structural formula, as a line, angle, or zigzag formula. As you look at the following slide, notice again how carbon always has 4 bonds. So in table 11.3, we have our butane. We have 4 bonds in every direction around carbon. Or if we condense it, we are going to have, again, 4 bonds around every carbon, or here's our zigzag line of our butane. So let's see if you can do this. Now, if we give you the following expanded structural formula, see if you can write the molecular formula, the condensed structural formula, and give us the name. Press pause and come back. Well, we look and see the molecular formula. 1, 2, 3, 4, 5 carbons. And so 5 carbons, and that means we have 12 hydrogens. We either count the hydrogens or we use the formula, which is 5 times 2 plus 2, which is 12. So the condensed structural formula is going to have CH3, CH2, 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 and then CH3. The compound name, it's got 5 carbons and all single bonds, so it's pentane. Write the condensed structural formula for ethane and heptane. Press pause and come back. Hopefully you did that. Alright, let's go on to the next one. Cycloalkanes. They are cyclic alkanes. Also they're ringed. The ring doesn't mean like a ring, but they're connected in a, I don't want to use the word circle because that's not all circles, but they're connected. No real beginning and end. So in order to make that connection, they're going to have 2 fewer hydrogen atoms than the open chain form. Because let's look at this propane compared to cyclopropane. Now then, in order to connect this carbon to carbon right here to make it in this cyclic ring, since carbon can only have 4 bonds, in order to connect this carbon to carbon, it's going to have to drop a hydrogen from here and a hydrogen from there, i.e. 2 less hydrogens to make this connection. So the formula for figuring out how many hydrogens there are in a cycloalkane is CnH2n. They are named by using the prefix cyclo before the name of the alkane chain with the same number of carbon atoms. So here's with C3H8 with propane. If it's the cyclic ring, it's cyclopropane. Now in table 11.4, it shows some formulas of some common cycloalkanes. So we have, let's just go directly down here to our line angle. Let's count the corners. 1, 2, 3. So this is going to be cyclopropane. Count the corners. 1, 2, 3, 4. Cyclobutane. Count the corners. 1, 2, 3, 4, 5. Cyclopentane. Count the corners here for the last one. 1, 2, 3, 4, 5, 6. Cyclohexane. So you will notice that as you look up other ways to show that, but quite often with the cyclic compounds, it is just so much easier just to draw them as the line angle formula, and so they're written that way a lot. So press pause and see if you can come back and do this. Alright, so here we have our zigzag chain. Let's count the ends and the corners. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8. They're all single bonds, so it's octane. Okay, so we have a cyclic ring here, so we're going to name it cyclic something. Let's count how many corners there are. 1, 2, 3, 4, 5. So cyclopentane. Press pause and come back and name these compounds. So 4 carbons is butane. This is a cyclo, and let's count the ends. 1, 2, 3, so cyclopropane. Let's count how many carbons there are here. 1, 2, 3, 4, 5, 6, 7, 8. All single bonds, so it's octane. This is a cyclic compound, so we're going to say cyclic. Let's see how many corners. 1, 2, 3, 4, 5, 6. Cyclohexane.